Now we'd like to find the power series representation for the function f of x equals the natural log of x squared plus 2. Again, we're using our geometric series that we know the sum from n equals 0 to infinity of x to the n power is equal to 1 divided by 1 minus x for values of x with an absolute value less than 1. So we need to relate our function, the natural log of x squared plus 2, to something of the form 1 divided by 1 minus something. So I realize that if I take the derivative of my function, I get a fraction. The derivative of a natural log is 1 divided by whatever's inside, x squared plus 2. And then the chain rule says I have to multiply this by 2x. Or dividing top and bottom by 2, we have 1 divided by x squared divided by 2 plus 1 times x. And once more, let's put that x in front. We have x times 1 divided by, I can write 1 plus x squared over 2, or 1 minus negative x squared over 2. And this is the form that I want. My geometric series tells me that 1 divided by 1 minus negative x squared over 2 is equal to the sum from n equals 0 to infinity of negative x squared divided by 2 to the n power. I can rewrite this as the sum from n equals 0 to infinity of negative 1 to the n power times x to the 2n power divided by 2 to the n power. Now, our function f prime of x is x times the function we just found a power series for. So that's x times the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, divided by 2 to the n power. And multiplying that x into each term, we have the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2 to the n power. Next, we need to find an expression for f of x. F of x is the antiderivative, or the indefinite integral, of f prime of x dx. In other words, the indefinite integral of this function defined by the power series. We have a theorem that says we can find the antiderivative of a power series term by term. So I can write this as the sum of the integral of negative 1 to the n, x to the 2n plus 1, divided by 2 to the n dx. Now I left this a little bit strange blank space in the beginning because typically when we integrate something we get that plus c. Well, for power series we usually just write the c in front instead of at the back. Now, finding the antiderivative of each term, the negative 1 to the n is a constant, the 2 to the n in the denominator is a constant, and I'm using the power rule. So I end up with x to the 2n plus 2 divided by 2n plus 2. I can do some simplification here. Notice that 2n plus 2 is 2 times the quantity n plus 1. So I can take that 2 that's out front and combine it with the 2 to the n that's also in the denominator. So we get 2 to the n plus 1 in the denominator times n plus 1. And I can do the same thing in the exponent of my x. We can write it as 2 times the quantity n plus 1. This is what we have so far. Now I'm noticing that I have a lot of expressions of n plus 1, so I'm going to shift the indices. I'm going to write this sum as the sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the 2n divided by 2 to the n times n. I have another video about shifting indices to help with that part. Now, this is not our final answer. Because our f of x is a specific function, the natural log of x squared plus 2, we cannot leave the plus c, the constant of integration, in our answer. What I'm going to do is plug in 0 for x. So I have f of 0 equals c plus the sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the 2n divided by 2 to the n times n. And setting x equal to 0 means I have a 0 right here. Because my sum starts at n equals 1, the exponent on x in each term is positive. So all of these terms are equal to 0. So we figure out that f of 0 is just equal to c. And then of course we can evaluate. F of x is the natural log of x squared plus 2. So f of 0 is the natural log of 0 squared plus 2, or in other words, the natural log of 2. Now plugging in our value for c, we figure out that f of x is equal to the natural log of 2 plus the sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the 2n divided by 2 to the n times n. Now we need to think about the radius of convergence. Let's look back at our previous slide. In this step, we wrote our function as a geometric series with common ratio negative x squared divided by 2. So for this step, we need the absolute value of negative x squared divided by 2 to be less than 1. If the absolute value of negative x squared divided by 2 is less than 1, that means that the absolute value of x squared divided by 2 is less than 1. Or in other words, the absolute value of x squared is less than 2, or the absolute value of x is less than the square root of 2. So the radius of convergence for our original series is the square root of 2. So this series has radius of convergence square root of 2. Now simplifying and multiplying a series by an expression that does not contain the index n does not change the radius of convergence. And the theorem in this section that says we can take the antiderivative of a power series term by term also says that the radius of convergence does not change. This tells us that our overall radius of convergence is equal to the square root of 2.